तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In today's lecture, we continue our discussion on sensitivity analysis. In the last lecture, we had seen the effect of changes in the objective function value for a non-basic variable as well as for a basic variable. This is the example problem that we discussed in the last lecture. This is the optimum simplex table. Earlier we first looked at change in objective function coefficient of a non-basic variable. We considered variable x2 and worked out. Then we looked at change in objective function coefficient of a basic variable. We made a change in x1 and we worked out the effect of the change. Today, first thing we would do is to see what happens to the solution if the right hand side values changes, one of the right hand side values changes or both can change. Now the right hand side vector is given by b equal to 9, 12. We now assume that this 9 is going to change to some value and therefore we start with b1 here and 12. Now if this 9 becomes b1, then the effect of this change will only be seen in the right hand side values. So these right hand side values will change. We now know that right hand side value is equal to b inverse b, and we have already seen that corresponding to the basis x3 x1 we can read b inverse directly from the simplex table. So you could read b inverse from 2 by 5 minus 1 by 5 minus 1 by 5 and 3 by 5 into b1 12. So the right hand side values will become 2 by 5 b1 minus 12 by 5 or 2 b1 minus 12 by 5, 36 minus b1 by 5. If b1 is such that both these are greater than or equal to 0, then we have the primal feasible as well as dual feasible, and the present set of basic variables will be optimal with the corresponding value here. For example, if we substitute b1 equal to 9, which is in the original problem, so 18 minus 12 by 5 is 6 by 5, 36 minus 9 is 27, 27 by 5 is what we have here. Now if which would mean that if 2b1 minus 12 by 5 greater than or equal to 0 gives 2b1 minus 12 greater than or equal to 0, b1 minus 6 greater than or equal to 0, b1 greater than or equal to 6. 36 minus 5, 36 minus b1 by 5 greater than or equal to 0 would give b1 less than or equal to 36. So as long as b1 is within the range 6 to 36, 6 less than or equal to b1 less than or equal to 36, the present set of basic variables will remain optimal with values 2b1 minus 12 by 5, 36 minus b1 by 5. We need to substitute the values of b1 in this to get the right hand side. Now if b1 violates this range, is outside of the range, then one of these will become negative. For example, when B1 is 40, if we take B1 equal to 40, then right hand side will become 80 minus 12 by 5, which is 68 by 5, and minus 4 by 5. So now if B1 is equal to 40, then this will change, and this will change to 68 by 5 and minus 4 by 5. Now the value of the objective function will also change. We do not write the value here because right now we have a negative here, which means we have an infeasible solution. Now this solution is infeasible, the primal is infeasible, but the dual is feasible. Therefore, we can perform a dual simplex iteration till we get to the optimum. So we leave out this variable, we compute theta. So minus 18 by 5 divided by 7 by 5, we do not evaluate theta here because there is a strictly positive value. Pivot element should have a negative. Minus 6 by 5 divided by minus 1 by 5 is 6. Here again we do not evaluate because of a positive value. There is only one candidate to enter. So variable x4 enters and replaces variable x1. Now that is shown here in this table. Now you realize that variable x4 has entered the basis and variable x1 leaves the basis, and we perform one dual simplex iteration, and at the end of the iteration we have a solution x3 equal to 12, x4 equal to 4, z equal to 48. The optimum solution after this change is x3 equal to 12, x4 equal to 4, z equal to 48, and it happens that within one iteration we are able to get the optimal solution for this. So wherever there is a change in the right hand side values, the effect of the change is seen in the right hand side value in the last iteration of the simplex algorithm. Now we need to evaluate that by doing this. Right hand side becomes B inverse D, and then for the given value, if one of them becomes negative, as we saw here, when B1 equal to 40, this became negative, and then we continue with dual simplex iterations till we reach the optimum. Now the next thing that we will see is what will happen if there is a change in the constraint coefficient of a non-basic variable. To do that, let us go back and write the original simplex table with the values here. Now let us consider a non-basic variable x2 here, and let us look at a change in the coefficient of this variable in any one of the constraints, which means we are looking at a change either in this 2 or in this 3. Now to do that, let us consider a change here. So this, let us assume that this number 3 becomes something else. So what happens here is P2 from the original problem now becomes 2 comma a. Now when this 3 changes to a value a, now what will happen to the optimum table? Now when this changes, when this becomes 2a instead of 2 3, now this will also change, because this is p bar 2 equal to b inverse p2 equal to b inverse p2. B inverse can be read from the table, so we get 2 by 5 minus 1 by 5 minus 1 by 5 3 by 5 into A, which will give us 4 minus A by 5, 2 by 5 into 2, 4 by 5 minus A by 5. So, 4 minus A by 5 minus 2 by 5 plus 3 by 5A. So, 3A minus 2 by 5. Now, because of this change, now this will become 4 minus A by 5, 3A minus 2 by 5, and because of this change, this C2 minus Z2 will also change. So, we evaluate C2 minus Z2 equal to C2 minus YP2, C2 is 3 minus Y can be read again from the simplex table. Y represents the value optimum solution to the dual. So, 6 by 5, 7 by 5 under the primal slack variables. So, 6 by 5, 7 by 5. Now, P2 has changed to 2A. So, this becomes 3 minus 12 by 5 minus 7A by 5, which is 3 by 5 minus 7A by 5. Now, if A is such that 3 by 5 minus 7A by 5 is negative, then this will become negative and the present solution will remain optimal. Such a change will not have any impact on the optimal solution. For example, for the present value of A equal to 3, we would get 3 minus 21 by 5, which is minus 18 by 5. Therefore, it remains as negative. If A is such that this term becomes positive, then this will become positive and a variable x2 will enter. So, if we consider, for example, A equal to 0, so if we consider A equal to 0, then C2 minus Z2 will be 3 by 5, P bar 2 will be 4 by 5, and when A is 0, minus 2 by 5. So, when A is 0, which means when this 3 becomes 0, then we will have 4 by 5 minus 2 by 5 and we will have plus 3 by 5. Now, because of this plus 3 by 5, variable x2 will enter the basis. We need to find out theta for the leaving variable. So, 6 by 5 divided by 4 by 5 is 3 by 2, 27 by 5 divided by negative, so we do not divide, this becomes dash, this variable leaves the basis. So, variable x2 enters and variable x3 leaves the basis. We need to do simplex iterations till we get to the optimum, and that is shown here. So, variable x2 enters with 3 by 5, Cj minus Zj equal to 3 by 5, and variable x3 leaves with theta 3 by 2, which is shown by the arrows, and in the next iteration we have x2 and x1 as basic variables with the solution x2 equal to 3 by 2, x1 equal to 6 and z equal to 57 by 2. The optimum solution is x1 equal to 6, x2 equal to 3 by 2 with z equal to 57 by 2. We get the optimum once again in one iteration for this example. In summary, if we have a change in the coefficient of a non-basic variable in any of the constraint, then that will be reflected by change in Cj minus Zj for that non-basic variable and change in the P bar in the corresponding column in the optimum simplex table. If the Cj minus Zj becomes positive because of the change, the variable enters the basis and we perform or continue to do simplex iterations till we get to the optimum. Now, let us look at one more thing here. Let us look at something called adding a new product. Now let us look at adding a new product. Now let us go back to the optimum simplex table that we had. Now, the original problem has 3 variables x1, x2, x3, and let us assume that these represent some decisions with respect to producing 3 products 1, 2 and 3 respectively. Now we have set up the problem and we have found out the optimum solution using the simplex algorithm. Now let us assume that we want to introduce a new product into this, and let us call that new product by a variable x6, because x4 and x5 will be the slack variables corresponding to these two. We now introduce a new variable x6 which represents a new product. A new product is characterized by its contribution in the objective function as well as the values in these two constraints. So let us assume that C6, which is the objective function coefficient corresponding to the new product x6, is given by 6, and the constraint coefficients in both the constraints 1 and 2, which is given as P6, is given by previous table 1 and 3. Now the problem becomes 4x1 plus 3x2 plus 5x3 plus 6x6 subject to x1 plus 2x2 plus 3x3 plus x6 less than or equal to 9, 2x1 plus 3x2 plus x3 plus 3x6 less than or equal to 12. Now should we solve the problem all over again because of the introduction of a new variable, or can we make these changes, see how the addition of a new product reflects itself in the optimum simplex table, and can we proceed from that? We can proceed from the simplex table. To do that, let us just create another column for x6, x6. The right hand side values will remain as it is, (6 by 5) and 27 by 5. Now we need to find out P bar 6 and C6 minus Z6. Now to do this, P bar 6, first we have to find out C6 minus Z6 to see whether there is an effect. So C6 minus Z6 is equal to C6 minus YP6, 6 minus C6 is 6, Y is the optimum solution to the dual, which can be seen under the primal slack variables. So 6 by 5, 7 by 5 with a minus sign of course, and P6 is the requirement of the resources 1 and 3, so 1 and 3. So C6 minus Z6 is now 6 minus 6 by 5 minus 21 by 5. So this is 6 minus 27 by 5, which is 3 by 5. So now if we can make a product 4 reflected by a variable x6, which can give us a unit contribution of 6 and requires 1 and 3 respectively of these resources. Now under the present optimal, because C6 minus x6 is positive, then this variable x6 will enter the basis and it is profitable to make the new product. So this becomes 3 by 5. Now this will enter. Now in order to find the leaving variable, we need to know these two values, which is the corresponding column in the optimum simplex table, which is your P bar 6. So P bar 6 is given as B inverse P6. We have already seen that any P bar j is B inverse Pj, P bar 6 is B inverse P6, B inverse is seen under the identity corresponding to the slack variables. In this case, variables x4 and x5 had the identity matrix. So B inverse is 2 by 5 minus 1 by 5 minus 1 by 5 3 by 5 into P6 is 1 and 3. So you get 2 by 5 minus 3 by 5 is minus 1 by 5 minus 1 by 5 plus 9 by 5 is 8 by 5. So you get minus 1 by 5, 8 by 5, this has 6. So now variable x6 enters the basis. To find out the leaving variable, we need to compute theta. 6 by 5 by minus 1 by 5, we do not compute theta because we have a negative number here. 27 by 5 divided by 8 by 5 is 27 by 8. So this variable leaves, variable x1 leaves, variable x6 enters. Now that is shown in the table here. So we started with x3, x1. When we introduce a new product x6 with objective function coefficient 6, you can see that above x6, and Cj minus Zj is 3 by 5 for the given values, contribution 6, requirement 1 and 3. We compute Cj minus Zj to 3 by 5 and variable x6 enters. We compute P bar j equal to B inverse Pj minus 1 by 5, 8 by 5, same values here that you see in that table. So variable x6 enters the basis and variable x1 leaves the basis. So the next simplex table has x3 and x6 with values 15 by 8 and 27 by 8. After one simplex iteration, objective function is 237 by 8 and the optimum solution is x3 equal to 15 by 8, x6 equal to 27 by 8, z equal to 237 by 8. So in this case, adding a new product is profitable and we add a new product. If it turned out that C6 minus Z6 were negative, then we will not enter variable x6 and say that it is not advisable to produce the new product and the present solution would remain optimum. Next thing that we will see is adding a new constraint. Now let us write the simplex table without the new product. Now let us look at this problem again, the same problem and the optimum solution. Now we have solved this problem for these two constraints. Now at the end, after getting the optimal solution, we realize that another constraint has to be included. Let us assume that inadvertently we have left out a constraint, or suddenly we realize that there is another resource that may be needed which has not been taken into account, which results in a new constraint coming in. Now if such a new constraint is introduced, once again we need to know whether should we solve the problem optimally, or is it possible to go back to the optimum table, make the changes with respect to the new constraint in this table, and whether we can proceed from here to the optimum. So let us consider a new constraint. Let us have a new constraint which is this. So we get x1 plus x2 plus x3 less than or equal to 8. So let us look at a constraint x1 plus x2 plus x3 less than or equal to 8 as a third constraint. If we look at this constraint, let us go back and see whether the optimal solution here satisfies this constraint. Now x1 equal to 27 by 5, x3 equal to 6 by 5, x2 is non-basic at 0. So x1 plus x2 plus x3 left hand side is 33 by 5, which is less than 8. So this constraint is satisfied. So when this constraint is satisfied, you could go back and say that this constraint will not have any impact on the optimal solution. The optimal solution will remain as x3 equal to 6 by 5, x1 equal to 27 by 5, z equal to 138 by 5. So when a new constraint is introduced, first thing we need to do is to verify whether the present optimal solution satisfies the constraint or not. If it satisfies the constraint, then in spite of the inclusion of the new constraint, the original solution will remain optimal. If on the other hand the new constraint had been x1 plus x2 plus x3 less than or equal to 6, then we realize that x1 plus x2 plus x3, the left hand side is 33 by 5, which is more than 6. So the present optimal solution violates this constraint, and because it violates this constraint, now this constraint will have an impact in the solution, and we need to do that. So let us do this here. So we write the new constraint as x1 plus x2 plus x3 less than or equal to 6. Now x1 and x3 are basic variables, so x1 and x3 are basic variables. So write the basic variables in terms of the non-basic variables. So x1 plus 1 by 5 x2 plus x3 plus 2 by 0 x1 plus 1 by 5 x2 plus 1 x3 plus 2 by 5 x4 minus 1 by 5 x5 equal to 6 by 5. 1 x1 plus 7 by 5 x2 minus 1 by 5 x4 plus 3 by 5 x5 equal to 27 by 5. So x1 is written from this equation as 27 by 5 minus 7 by 5 x2 plus 1 by 5 x4 minus 3 by 5 x5 plus x2. Now x3 is written from this equation as plus 6 by 5 minus 1 by 5 x2 minus 2 by 5 x4 plus 1 by 5 x5 less than or equal to 6. Now let us go back and look at all the right hand side values. 27 by 5 plus 6 by 5 is 33 by 5. We take it to the other side, you get less than or equal to minus 3 by 5. Now let us look at all the x2 values. Minus 7 by 5 plus 1 is minus 2 by 5, minus 2 by 5 minus 1 by 5 is minus 3 by 5 x2. Let us look at x4. Plus 1 by 5 minus 2 by 5 is minus 1 by 5 x4, and let us look at x5. Minus 3 by 5 plus 1 by 5 is minus 2 by 5 x5 less than or equal to minus 3 by 5, or the less than or equal to constraint. So we add a slack variable to convert it to an equation. We get minus 3 by 5 x2 minus 1 by 5 x4 minus 2 by 5 x5 plus x6, which is now the slack variable to convert this to an equation, equal to minus 3 by 5. So this is how the new constraint gets reflected in this table. Now we include this into this table to get, we add another row here with variable x6, which is slack variable, comes in. We add another column here for variable x6. The right hand side values will remain the same, 6 by 5, 27 by 5, 138 by 5. The Cj minus Zj values will remain the same, 0, minus 18 by 5, 0, minus 6 by 5, minus 7 by 5. Now we write this constraint. So this is 0 x1 minus 3 by 5 x2, 0 x3 minus 1 by 5 x4 minus 2 by 5 x5 plus x6 equal to minus 3 by 5. Now these two will not have x6, so x6 will have 0, 0, 1 identity column. X6 will be introduced here. It is a slack variable with an objective function coefficient of 0, objective function coefficient of 0, and Cj minus Zj of 0. So if the new constraint is binding, as it is in this case, if the new constraint is violated by the existing optimal solution, then this will get reflected as another constraint in the simplex table. Now important thing is that when we write this and when we introduce a slack variable which becomes a basic variable with the identity column, then we will have a negative value here. Now this negative value indicates that the present constraint is binding, or the newly introduced constraint is violated by the existing optimal solution. For example, if we had x1 plus x2 plus x3 less than or equal to 8 with which we started, which was satisfied by the present optimal solution 6 by 5, 27 by 5. So we said when a new constraint is introduced, the first thing to do is to check whether the new constraint is satisfied. Only if it is violated, we go back, write it in terms of the existing basic variables and write this equation. In case we had not checked whether it is violated or not, for example, if we had simply taken this 8 here and carried out this exercise, then you would realize that we would have a positive value here, which means that the present solution is optimal. So when the constraint is satisfied by the present optimal solution, we leave it as it is, or even if we take the trouble of converting it and seeing its effect in the simplex table, we would get a feasible solution here indicating optimum. So only when the newly added constraint is violated by the present optimal solution, we will get a negative here, and that is when we do this exercise to get a negative here. The negative here is a check for us that this constraint is not satisfied by the present optimal solution. Now with this we perform a dual simplex iteration because the feasibility conditions are affected, the optimality condition remains intact, so we perform a dual simplex iteration. So variable x6 leaves the basis, and we need to find out an entering variable which is theta. Now to do that, we go back and check minus 18 by 5 divided by minus 3 by 5 is 6, minus 6 by 5 by minus 1 by 5 is 6, minus 7 by 5 divided by minus 2 by 5 is 7 by 2. So for all the 3 negative Cj minus Zj values, we have negatives here, so we compute the theta, and then we enter the variable which has minimum theta. So variable x5 enters the basis, x6 leaves the basis, and we do a dual simplex iteration. So that is shown here. Now the effect of the constraint, the first thing we did is we verified that this constraint is violated by the present optimal solution. So we did all these calculations or computations and then wrote the new constraint. Now that is reflected here as an additional third constraint in the optimum table. It is also shown here. Now this results in an introduction of a new row corresponding to the new constraint, as well as a new column corresponding to a slack variable associated with the new constraint. So we have one more row and one more column. The slack variable becomes a basic variable here, and the corresponding right hand side is negative, which is a check which indicates that the newly added constraint is binding and is violated by the present optimal solution. Now we go back and then perform a dual simplex iteration by leaving out variable x6 and entering variable x5, and within one iteration we get the solution. Optimum solution is x3 equal to 3 by 2, x1 equal to 9 by 2, and x5 equal to 3 by 2 with z equal to 51 by 2, which is shown here. Now there is one more aspect of sensitivity analysis which we have to look at, which is what happens to change in constraint coefficient of a basic variable. Now when we do that, we go back and write the optimum table as it is. Now the last thing that we need to look at in sensitivity analysis is what happens if a constraint coefficient of a basic variable changes. For example, we have variables x1 and x3. x1 has coefficients 1, 2 in the two constraints, x3 has coefficients 3, 1 in these two constraints. Earlier we looked at change in constraint coefficient of a non-basic variable. We took variable x2 and we said if this changes to a, what happens and so on. Now we are looking at what will happen to the problem if, for example, this number changes, or this, or this, or this. Now when any of these changes take place, that is, if a basic variable's coefficient in a constraint changes, then the answer is do not perform sensitivity analysis, solve the problem all over again. Only in this case, when there is a change in the coefficient corresponding to a basic variable in any constraint, the answer is do not perform sensitivity analysis, do not try to see the change in this, but solve the problem all over again. Why? So far in all the things that we saw, so far we have seen many aspects of sensitivity analysis. So let us write all those here. The various aspects that we have seen in sensitivity analysis: change in objective function coefficient of non-basic variable, to changes in objective function coefficient of basic variable change in right hand side values, constraint coefficient of non-basic variable, adding a new product and adding a new constraint. In all these 6, we reflected the changes in the optimum table and continued either with simplex iterations or dual simplex iterations. The reason we could do this was the B inverse was intact. Any of these change did not change the basis corresponding to x3, x1. Now any one of these 6 changes would still keep the basis corresponding to x3, x1 as 3, 1, 1, 2. The basis remained intact. These changes did not affect the basis. Because these changes did not affect the basis, these changes were reflected either as changes in the right hand side values or effectively changes in the Cj minus Zj. Now these changes could be written in terms of B inverse. Right hand side values were B inverse B, Cj minus Zj was Cj minus Cb B inverse Pj. B inverse did not change, and B inverse could be read from the optimum simplex table. Now when we make a change here, either here or this or this or this, the basis changes, and because the basis B changes, B inverse changes, which means every element in this would change, and there is a likelihood that we may get a negative here as well as a positive here. We may have a situation where both the feasibility and the optimality condition could be violated. Whereas with all these changes, if at all there is a violation, it would be either the feasibility violation or the optimality violation. Now because of the possibility that due to change in basis, B inverse changes and the entire matrix changes, which could give us, for example, a situation where we have infeasibility here and non-optimality here. So we do not want to start with a matrix which is both infeasible as well as non-optimal. So it is customary that we do not perform sensitivity analysis if we have constraint coefficient of a basic variable changing. So let us go back and summarize the various aspects of sensitivity that we have seen. We have seen 6 aspects of it. So if there is a change in the objective function coefficient of a non-basic variable, that gets reflected in Cj minus Zj value of that variable, and the only thing that could happen is that variable could enter the basis. So we looked at simplex iterations till we reach the optimum. Objective function coefficient of a basic variable would be reflected in Cj minus Zj of all non-basic variables, and then we could do a simplex iteration to solve. Changes in right hand side would mean changes in the right hand side again. In the optimal solution we could get a negative right hand side, so we used dual simplex iteration to solve. Constraint coefficient of a non-basic variable would mean Cj minus Zj of that variable, and if that variable enters, we looked at a simplex iteration. Adding a new product would mean Cj minus Zj of that product which is presently non-basic. So presently non-basic, and we could use simplex to proceed. Adding a constraint would mean constraint violated, so right hand side negative, and we could use dual simplex. Now that is summarized in this table. So we have this table summarizing the various changes that could take place, that could be modeled in using sensitivity analysis. These are the 6 that we have seen, and these are the corresponding methodologies which you could go to simplex or dual simplex respectively. Now all these 6 changes were possible because, as we said, the B inverse did not change, the basis did not change, B inverse did not change, and B inverse could be read from the optimum simplex table. Now we know that for a maximization problem, when the optimum simplex table is known, then we could read the B inverse from where we had the identity matrix in the first iteration. For example, if we had started this problem from the beginning, we would have seen variables x4 and x5 would be the slack variables, and they would be the initial basic variables. So under x4 and x5 you could see B inverse. Now if we had a minimization problem with all greater than or equal to, then we need to know where in the simplex we could see the B inverse. So if we had a minimization problem, then our simplex iterations would look like this. For example, if we had a minimization problem, say with 3 decision variables, then we would have had x1, x2, x3, x4, x5, a1, a2 and right hand side. We would, assuming we would have had greater than or equal to constraints, then we would have added 2 artificial variables. So we would have started the simplex iteration with a1, a2 with the coefficients here with a minus 1, 0, 0, minus 1 under slack, and a 1, 0, 0, 1 here with the right hand side. So under the artificial variables in the optimum iteration you would see B inverse if we did or used a big M method to solve. So if we, assuming that we either have problems with all less than or equal to constraints, or if we had any other combination, then we would be using the big M method to solve. Then wherever we had the identity in the original table, then under that table you would see. For example, if this is the last table, then your B inverse will be here, and because this had a minus I, you would have a minus B inverse under the slack variable. So, this is something that we need to know if we want to do sensitivity analysis using the matrix method that we have seen. So, B inverse, the location or where we find B inverse in the simplex table is something that we need to know. If we have an all less than equal to constraint problem, which means the slack variables would become the starting basic variables. So, under the slack you would have like we had here under x4 and x5. If we had any other combination of constraints either mixed or with greater than or equal to, then we would be adding suitable artificial variables and using the big M method. So, wherever we had the identity matrix, we would see the B inverse under that. If we had only greater than or equal to, then both the artificial variables would qualify to be the basic variables, in which case the artificial variable portion will have the identity matrix, the slack variable portion will have minus I. So, under the artificial variable you would see B inverse, under the slack you would see minus B inverse. So, in summary, we use sensitivity analysis to try and evaluate changes in the problem. So, we need not solve the problem all over again if there are changes in the objective function coefficients, both basic variable and non-basic variable, if there are changes in the right hand side, if there is a change in the constraint coefficient of a non-basic variable, if we add a new product, which means we add a new variable into the problem, and if we add a new constraint, and if the constraint is binding. In all these situations, the 6 situations that we have seen, we need not solve the problem all over again. We could reflect the changes that have taken place in the problem into the optimum simplex table using the matrix equations and proceed from the optimum simplex table either by using a simplex iteration or a dual simplex iteration depending on where the change is. The only situation where we need to work out the problem all over again is when there is a change in the constraint coefficient of a basic variable. For our example, since x3 and x1 are basic variables, if there is any change in the constraint coefficient either here or here or here or here, then we need to solve the problem all over again. Now, this brings us to the end of what is the linear programming portion of the course. So, let us spend a couple of minutes for a quick recap as to the number of things that we had learned in the linear programming portion of this course. So, first thing we did was we learnt the formulation. In the formulation part of the course, we learnt how to write or convert a real life situation into a mathematical model, and then we defined the linear programming problem. We defined the basic terminology such as decision variables, objective functions, constraints and non-negativity. And then we said a problem is called linear programming problem if it has a linear objective function subject to linear constraints and non-negativity restriction. We also classified or found out that we could have 2 types of objective functions, maximization and minimization, 3 types of constraints, less than or equal to, greater than or equal to and equation, and 3 types of variables, greater than or equal to, less than or equal to and unrestricted. Then we looked at solving the linear programming problem. Under solution we saw 3 aspects: the graphical method, which is applicable to a 2 by 2 problem or applicable to any 2 variable problem irrespective of the number of constraints. We saw the algebraic method, and then we saw the simplex method. We saw the graphical method, we found it suitable if there are 2 variables, and then we said we needed a method which can handle more. Then we looked at the algebraic method which evaluates all basic feasible solutions, and then we looked at simplex which does not evaluate all basic solutions, evaluates fewer than the many basic feasible solutions and then improves as we proceed. And then we continued our discussion on the simplex by looking at initialization, iteration and termination aspects of the simplex algorithm, and then we also learnt how to standardize or how to initialize into a simplex table if we have mixed type of constraints and mixed types of variables. Under iteration we learnt degeneracy, and under termination we looked at alternate optimum, unboundedness and infeasibility, and a bit of cycling of course. So we looked at the three aspects: alternate optimum, unboundedness and infeasibility. Later we looked at duality, which is, and showed that every linear programming problem has another associated problem called the dual of the linear programming problem. And we also said that the given problem is called the primal and the other problem that we write is called the dual. And then we also saw how to write the dual for different primals given, or if the primal has, for example, a minimization, mixed type of constraints and different types of variables. And then we looked at duality theorems. We looked at the weak duality theorem, optimality criterion theorem and the main duality theorem. We also had an economic interpretation of duality. We said what the dual variable means physically, mathematically, algebraically, etc. And we also saw the dual simplex method, and dual simplex method that can be used if we have all greater than or equal to constraints. And then we also, for example, in duality we looked at the relationship where the primal and the dual will have optimal solutions. If they have optimal solutions, then they will have, the optimal solutions will have the same value of the objective function. And then we also said that if primal and dual have feasible solutions, then both have optimal solutions with the same value of the objective function, etc. And then that also brings us to the relationships between unboundedness and infeasibility as far as these problems are concerned. For example, if the primal is unbounded, the primal maximization problem is unbounded, then the dual is infeasible, and if the primal is infeasible, then the dual is unbounded or infeasible. So we did not see these results explicitly earlier, but these also follow as a result of our discussion on duality. So from the duality theorems one can understand that if the primal, which is maximization problem, is unbounded, then the dual is infeasible, and if the primal is infeasible, dual is either unbounded or infeasible. So under duality we also looked at the dual simplex algorithm. Dual simplex algorithm that helps us solve problems with all greater than or equal to constraints, an algorithm which assumes or which can be used if the optimality condition is satisfied and the feasibility condition is violated. And then we also learned the complementary slackness conditions, and we said that the simplex algorithm not only solves the primal but also solves the dual and can give the optimal solution to both primal and dual. And then we applied the complementary slackness to all intermediate iterations of the simplex and showed that every non-optimal intermediate iteration of the simplex corresponds to a situation where the corresponding dual is infeasible. And we also showed that the Cj minus Zj, which is the extent of non-optimality or the extent to which we can enter a variable, represents the extent to which the corresponding dual is infeasible, and so on. From duality we moved to sensitivity analysis, and in sensitivity analysis we saw what we would do if there are changes in the problem, and we modeled 6 possible changes: changes in the objective function coefficient for the basic variables as well as the non-basic variables, changes in the right hand side, changes in the constraint coefficient of a non-basic variable, and adding a new product and adding a new constraint. So we have seen all these aspects under linear programming. The next thing that we would see are 2 very interesting problems which are linear programming problems, but they have special algorithms to solve them. Now these 2 are called the transportation problem and the assignment problem. So we look at these 2 next. We have something called the transportation problem, and we have something called the assignment problem. Now we will be looking at both these problems in detail. Now both of them are interesting linear programming problems. Both of them can be formulated or modeled as linear programming problems, but they are not solved using the simplex algorithm directly. So special algorithms are developed to solve both these problems, the transportation as well as the assignment. Now in the next few lectures we will be going through these things in detail. However, let us start the transportation problem and try to formulate the problem today. Now what is the transportation problem? The transportation problem is as follows. So let us assume that there are a certain number of supply points and certain number of demand points. For example, let us assume that there are 3 supply points which we write here and there are 4 demand points. Now we are interested in supplying a single product that is available in different quantities in each of these supply points to each of these demand points. So we, in the transportation problem, we supply a single product or a single item is transported from the supply points to the demand points. We assume that a certain number is available in each of the supply point. So we assume that A1, A2, A3 are the supplies available in points 1, 2 and 3 respectively, or in general AI is the quantity that is available in supply point I, in our example I equal to 1 to 3. We also know the requirement, we call these requirements as B1, B2, B3, B4 or in general Bj as the requirement in the demand point j. And it also takes some money to transport from the supply point to the demand point. We right now assume that it is possible to supply from every supply point to every demand point. For example, we can supply here, supply here, you can supply here, can supply here. Similarly, one could supply to all the 4 demand points. And there is a cost of supplying one quantity, one item from I to j is given by Cij. In this case, this is C12 or C11, this is C12. For example, this is C31, this is C34 respectively. So cost of unit transportation from I to j is given by Cij. So the problem is this: given a certain supply points, m number of supply points, I equal to 1 to m, given a certain number of demand points, n demand points, Bj, j equal to 1 to n, where Ai is the supply available at point I, Bj is the requirement of point j. Unit transportation cost is Cij from point I to point j. How do we transport from this? So the formulation would be like this: Xij is the quantity transported from I to j. Now as far as every supply point is concerned, we write this. So sigma Xij less than or equal to Ai. If I take a supply point I, then whatever that goes from the supply point should be less than or equal to I. So j equal to 1 to n is less than or equal to Ai. Ai is the supply in point I. This is the quantity that goes out to each of the destinations. Similarly, whatever that enters destination j, now I equal to 1 to m, this is what comes into each of the destination point, that should be greater than or equal to Bj. For example, B1 is the requirement here, so whatever comes from these should be greater than or equal to Bj. This is for j equal to 1 to n, this is I equal to 1 to m. Xij greater than or equal to 0 and the objective function is to minimize the total cost of transportation, which is double sigma Cij Xij. Xij is the quantity that goes from I to j, Cij is the unit cost of transportation from I to j. So, this is summed over I equal to 1 to m, j equal to 1 to n Cij Xij. Now, this is the formulation of the transportation problem, and this is a linear programming problem with a linear objective function and linear constraints and an explicit non-negativity constraint. Now, we will look at understanding the transportation problem further and trying to solve the transportation problem in the next lecture.